So in the next few lectures, we will look at a very powerful technique for designing algorithms called dynamic programming. So the starting point of dynamic programming is to consider what we would call inductive definitions. Now there are many very simple functions which we come across which are inductive. So we all know that mathematically n factorial is n times n minus 1 factorial. Right? So we can write an inductive definition of factorial as follows. The base case, okay, is when n is 0, and in this case the factorial is 1. So f of 0 is 1. And in general, if we have n greater than 0, then f of n is given by n times f of n minus 1. In other words, we express the factorial of n in terms of the same function applied to a smaller input. Now this kind of inductive definition is not restricted only to numeric problems. You can also do it for structural problems. So for example, in a list or an array, you can consider a sub-list or a sub-array as a smaller problem. So here is a very simple way of describing insertion sort. So if I want to sort n elements, right, then the way insertion sort does is that, of course, if there is nothing to sort in the base case, then we are done. Otherwise, we look at the rest of the list starting from the second element and we recursively sort it, right? And then we insert the first element into the sorted list. So the insertion sort applied to x1 to xn requires us to insert the value x1 in the recursively sorted x2 to xn. So again we are applying the same function that we are trying to define to a smaller input, and in the base case, the smallest input, namely the empty one, we have an answer which is readily available to us. So one of the attractions of having inductive definitions is that they yield in a very natural way recursive programs. So we don't have to think much. We can almost take the inductive definition and directly translate it as a program. So here is a translation for factorial which more or less reflects the structure that we had before. Remember, the structure that we had before that was that f of 0 is equal to 1 and f of n is equal to n times f of n minus 1. Right? So we say if n, now just to make it a little more robust so that people give negative numbers, we give sensible answers. Instead of just checking n equal to 0, we can just check for any value 0 or less, we will just return 1. Right? If somebody asks us for factorial of minus 7, we are just going to return 1. But the expected thing is that they will start with 0. And then if they give us a positive number which is bigger than 0, then we will go to the recursive case. So we will compute factorial for n minus 1, multiply by n, and then return this answer. Right? So there's a very direct one-to-one correspondence between this inductive definition and the recursive program, and that's what makes inductive definitions very attractive from the point of view of describing a function, because the inductive definition can be mathematically justified and then the program is obviously correct, obvious in quotes, because it follows directly from the recursive or the inductive definition. So what such inductive definitions exploit is what is sometimes called the optimal substructure property. So what this complicated phrase means basically is what you expect from an inductive definition, that is, you solve the original problem by combining solutions to subproblems. Right? So the solutions to the original problem are derived in terms of solutions to the subproblem, and in particular if the subproblem is the same type, then it's computing the same type of answer. Now in a numerical question like factorial, it doesn't make sense to say something is optimal. But for example, when you're doing insertion sort, then certainly when you sort the sublist, the result of that is what you want for that sublist. Okay? So this gives rise to the notion of a subproblem. Right? So factorial of n minus 1 is a factorial subproblem of factorial of n, obviously. But it just so happens that factorial of n only required factorial of n minus 1. Now we could have problems which require more than one immediately smaller subproblem. For instance, factorial of n minus 2 is also a subproblem. N minus 3 is also a subproblem, and so on. Right? So any smaller input can be treated as a subproblem of the original thing. Likewise, when we actually do insertion sort, we give it the input x1 to xn and we ask to sort x2 to xn. Right? So this is the subproblem which is directly part of the statement. But in general, one could think of any segment xi to xj to sort as a subproblem of sorting. Right? This would happen, for instance, in something like merge sort or quick sort, especially in merge sort, where you break up the array into halves and then into quarters and so on. So at any given point, you're applying the same algorithm to some segment from AI to AJ. So now let's look at a problem that we have seen before, okay, in the context of greedy algorithms. So we looked at this problem called interval scheduling. So interval scheduling said that we had a resource which is available over a period of time, right? And now people will come and make bookings for the resource. So somebody may want to book it during this segment, somebody else may want to book it during this segment, somebody else may want it during this segment, and so on. Now during these overlapping things, you cannot give the resource to two people, right? So you are given a set of requests, each with a starting time and an ending time. So we have a start and an end or a finish time. And now what you want to do is decide which of these requests you can allocate so that the maximum number of bookings are actually granted, right? So the goal is to maximize the number of bookings, not the length of the bookings, but the number of bookings. So in this particular case, what happens is that when you honor a booking, now if a booking happens to be overlapping with a few other bookings, okay, then if I decide to take this booking, then this goes away, right? So these two bookings which overlap with it can no longer be scheduled because they conflict with this in some time interval. So therefore now we have to solve or find a way of allocating the remaining bookings for some subset of the bookings, right? So each subset of the bookings is a sub-problem in this case. And the strategy that we saw was a greedy one, which said to pick the one which has the earliest finishing time, right? So among all those bookings which are still available to us to allocate, we pick one in a greedy way by just looking at it among all those that remain the earliest finishing time. Now this, as we said, when we add, will eliminate some bookings which are in conflict. That gives us a sub-problem, and we will solve this sub-problem. Right? So how many sub-problems are there? Now we have n bookings, and every possible subset of this is a sub-problem. So we have an exponential number of sub-problems. Right? In general, we have any possible subset could be our answer. So we have to look through all these exponential things in principle in order to find the best allocation, the one that gives the maximum number of bookings to be satisfied. Now what our greedy strategy does is effectively it cuts down this exponential space into a linear space, because what it does is it will pick, so we have initially bookings 1 to n, then it will pick among these, let's assume they are actually sorted by order of the earliest finishing time. So you will take the first one and then you will rule out a few from there. Okay, and now you will have some remaining, and then among those you will pick the earliest one. Okay, and then you will rule out a few more and so on. So at most you will allocate all n of them, but at each time once you include one, you will rule out a few. So certainly in a linear scan you would look at only that many subproblems. So you would only look at order n subproblems and find what you claim is an optimal answer. And since you are doing such a drastic reduction from 2 to the n to order n, obviously there is a question as to whether you have overlooked some subproblems accidentally by not examining them at all. So you need a proof, right? So that's why in a greedy strategy, you need to prove that what you are doing actually makes the solution come out to be correct, because you are really not looking at you're not considering a large number of subproblems. So suppose we change the interval scheduling problem very slightly. Okay? We associate with each request a weight. Okay? A weight could be, for example, the amount somebody is willing to pay. Okay? So maybe people are trying to book. So we have an auditorium which we rent out for performances and other activities, and people who come to use it are willing to pay to use it. Of course, there is only one auditorium, so two people cannot use it at the same time. Now our earlier goal was to maximize the number of bookings that we gave, but now we have another criterion which is more immediate, which is how much each person is willing to pay. So even if we give it to only one person, if that person is paying a lot more than everybody else, then that would be optimum for us, right? So now our aim is to maximize the total weight, right? So we want to get as much revenue as possible from our allocation, right? Not the number of bookings, but the total weight. So recall the greedy strategy in the earlier case, we wanted the earliest finish time, right? So if we saw this particular selection of 3 three requests, then the earliest finish time would be this one, right? So we would first take this, that would rule out this, and then because the third job starts or third request starts after the first one completes, so we will take this, and so we will get two bookings. Okay, and this 2 out of 3 is the best we can do, and that was fine in the unweighted case, right? But now unfortunately what we have is that we have a weight, right? So we have this weight associated with this. So we have to do something a little more clever, because now if we choose the first one and the third one, then the total weight is only 2, right? So job or not job, but let's call it booking 1 plus 3 gives a weight of 2, whereas booking 2 alone gives a weight of 3 because it has a weight 3, right? So ideally in this situation we should recognize that the middle request has enough weight to overcome the penalty of it being the only one that will be scheduled. So though we only get 1 out of 3 requests scheduled, we actually get a maximum benefit from the cost perspective, right? So therefore what this means in other words is the greedy strategy which we proved for the unweighted case is not valid anymore, unfortunately. So what shall we do? So one strategy is to see, is there another greedy strategy? We can search for another greedy strategy and try to argue that it works. And arguing that it works, as we saw, is rather, it takes a little bit of effort because we have to use an exchange argument or some such thing to prove that it is better than any solution that you could get by any other strategy. So the other approach, which is what we are going to look at in more detail in the next few lectures, is to try and look for an inductive solution which is obviously correct, but which can be evaluated efficiently, right? So the goal is to save. So what we are going to save is this effort in proving that by looking only at a few cases, we are actually producing an optimal answer. We will, in some sense, look at every case, but we will look at every case in a clever way, right? And that's what we are going to do. So how do we do this for this problem? Okay, so this time let's do something which is more direct than what we did last time. Instead of looking at the earliest finishing time, just look at the earliest starting time. So let's assume that our tasks or our requests are all ordered like this. Right? So we pick them up in this order. So we will begin with the first booking, which you call B1. Okay? Now observe that in the final answer, either B1 is there or B1 is not there. Okay? So we will take two options, right? So yes, B1 and no B1. Now if we eliminate B1, right, then our subproblem just consists of B2 onwards. Right? So we just have a subproblem which says B2 to Bn. So if we exclude B1, then we just use B2 to Bn, right? So exclude B1 means just throw it out and pretend you only had n-1 jobs to begin with. On the other hand, if you include B1, then you have to be a little bit careful, right? Because now if I include B1 in this particular thing, right? So if we include B1, then we have to rule out something which is in conflict, right? So we eliminate all the conflicting requests as we did in the greedy case, and then we have another subproblem which is not necessarily B2 to Bn, it will be some subset of B2 to Bn, right? But we have now taken both options. We have included B1 and excluded B1, so it's more reasonable to expect that we have either a solution with B1 or without B1. There's no third option. The solution either has B1 or doesn't have B1. We are trying to evaluate both, and then we are trying to choose the best one. Right? So this is an inductive decomposition of the problem into two subcases with B1, without B1. We are not making any predictions about which is better. We evaluate both and take the better one. Okay. So now let's argue that this kind of strategy actually considers all the options. Right? So just like B1, for any Bj, right, the solution either has Bj or does not have Bj. Right? This is very clear. So there are 2 to the n possible solutions, right? I could either have B1, not have B1, have B2, not have B2, right? So I can try every possible subset. That would be a brute force argument. We want to avoid having to try every possible subset. Now, for B1, we have clearly checked both cases explicitly. What about B2? Can we be sure that we are checking all cases of B2? Okay, so let's look at B2. Now, if B2 and B1 are not in conflict, that is B1 and B2 are in disjoint intervals, then whether or not B1 is chosen is independent of whether or not B2 is chosen. This means that whether we choose B1 or B2, the resulting subproblem would still allow us to choose B2, right? So whether we choose B1 or B0 at the B1 or not B1 at the beginning, right, it will be considered in both subproblems. And when we solve that, we will take both choices. On the other hand, if B1 and B2 are not compatible, that is B1 rules out B2 or because they overlap, then when B1 is chosen, B2 cannot be there. Right? So B1 can be there only if B2 can be there only if B1 is not there. So when B1 is chosen, we will not consider B2. But when B1 is not chosen, remember that we get the resulting subproblem of B2 to Bn. Right? So again, B2 will be chosen or given a choice. Right? Therefore, B2 we will consider all options in the presence or absence of B1. Likewise, we can argue that B3 will be considered in the presence or absence of B1 and B2. And what is happening is, as we are going along making more and more commitments, we are ruling out a lot of incompatible combinations which we would otherwise blindly consider if we did 2 to the n. Okay, now we still have to evaluate this efficiently, but at least it is not that difficult to believe that we are actually trying out every possible option. We are not in advance deciding that some local criterion like in a greedy strategy is enough to rule out certain subproblems as being useless. So the computational challenge comes from the fact that the subproblems that we generate may appear again and again. So let's look at a simple case. So supposing we have the picture that is shown below, right? So we have B1 and B2 which are in conflict, okay? But notice that both B1 and B2 are compatible with everything that comes afterwards, right? So if we choose B1, then we have to rule out B2. And so the subproblem we get is B3, B4 up to Bn. On the other hand, if you rule out B1, as we said before, you will try out everything that remains, namely B2 to Bn. Now what happens when you try B2 to Bn? Okay. So now when you come to B2 to Bn, you have to discard B2 or you have to keep B2. So supposing you discard B2, then what happens when you discard B2 from here? You precisely get the remaining part, which is B3 to Bn, right? So you again generate a B3 to Bn problem, which you had already asked once in the context of choosing B1, right? So we now have that you have choose B1, say yes, no, right? If you choose B1, I get this problem which is B3 to Bn. Then if I choose no, then I get a chance to choose B2, again yes, no, okay? And now if I don't choose B2, then I discard B2, again I get B3 to Bn. Right? So I will be solving this problem once here and once here unless I do something clever. Right? So the whole problem with this approach is that the inductive solution can give rise to the same problem at different stages. And if we just use recursion, as we said before, one of the great benefits of having an inductive definition is that you can just write a recursive solution which just mirrors the inductive definition of the problem. But if you do it naively, every time you come to the function to be done inductively, you will recursively call that same function, even if you have done it before. And this can be very expensive, as we shall see. Right? So the goal of dynamic programming is to avoid this wastefulness. Right? So there are two techniques that we will see. There is a technique called memoization, which is a way to build in some cleverness into recursion so that you never call the same function twice recursively. And dynamic programming will then be a way to avoid doing this recursive calls altogether. So dynamic programming is a way to enumerate the subproblems directly and solve them, knowing that the subproblems have some dependencies which you can predict. Okay, so we will look at these two techniques in the next couple of lectures and look at several examples to get familiar with these notions of memoization and dynamic program, which are essentially ways of making inductive definitions and the corresponding recursive implementations efficient to solve.